Of course, one of the most exciting things going on in racing today has to do with track surfaces. Dr. Mick Peterson of the University of Maine has worked with several groups on a very, very sophisticated project, and he's going to talk to us now about track surfaces. Dr. Peterson.
Thank you. We'll see if this shows up here. Yes. One more step and I'll be able to see it too. Yeah, the Mac users will mess it up for all of us. I want to start out by showing a little non-quantitative historical perspective on track surfaces. I'm probably the only person who buys horse racing books and sits there and looks for the harrows and the track maintenance and the pictures of looking down at the dirt. But this is out of a 1958 picture of Belmont. And if you look at that, the question is, when was the last time they harrowed that track? This is at the wire. You look at the way the hooves are cutting into that surface, it looks like they're running on the base, and they've got a pretty good chance of hitting a hoof print from the race before, or whether that was the training in the morning or when they harrowed that track. And then if you look behind them, you see that cloud of silt, which to me suggests that they weren't necessarily even controlling what the composition of that track was. Keep in mind that's 1958. If you think about that in the perspective of Larry's data, yes, the question is the problem the track surfaces. I think we can safely say the track surfaces have improved over the last half century. At least there's consistent use of the harrow. We've got some development of standard track designs, and most tracks make use of particle size separation so they can tell you their sand, silt, and at least from a particle size characterization. We're also at the beginning of an era of some dramatic new changes in both standard track designs as well as synthetic tracks. However, as was previously pointed out, we've had some dramatic differences over that 50 years in the tracks. I want to give credit to the other people who've worked with me on this, because this has had a lot of factors involved in this work. And from the beginning, it's had both trainers, veterinarians, sports scientists, as well as 2 track superintendents who were involved in this from the very beginning. I also want to reiterate, and this was almost unnecessary in the context of this talk, in this venue, but tracks certainly impact the racing from the safety as well as the fairness and consistency. And I hope that we can identify issues where they can help extend those careers. So even if tracks aren't necessarily the cause of the problem, if they can be a part of the solution. The projects I'm describing are not biomechanics research projects. We're making use of and applying work that's been done at Penn, UC Davis, and Colorado State. What we're trying to work with is develop the track management tools that are necessary to support tracks and the training centers to protect the horses. We've developed a test machine for evaluating tracks, and I recognize some faces out there, and if you'll bear with me, there is some what I consider some pretty dramatic new results that we're beginning to get. But our premise from the beginning is that because of these materials that are used, and it's more true, or at least as true with the synthetic tracks as it was with the traditional track designs, we have to match the acceleration speeds and loads of the tracks of the horse in order to measure the track surfaces. All of these surfaces are what we call nonlinear, strain rate dependent materials. So if we don't load it with the full load of the horse at the speed at which the horse loads the track, we won't get the properties that we need. Also, our philosophy is that we've tested the tracks with a machine, not an animal. The basic biomechanics work all has to be based on the horse. However, in order to measure a track from day to day and compare that data, the horses can't consistently track it. And then our baseline has been starting out working on what we consider to be a range of tracks, some of the best tracks in the countries, and try to figure out what is a good track. Longer term, the only way we can ever answer these questions is with epidemiological data. The epidemiological data in this area is completely lacking as far as I know. And there's been what would be characterized as pilot studies, but nothing beyond that. So what we've got is a perfect horse gate to load a perfect track, and now we need to begin to think about how that impacts the horse. Stepping back to define some terms that I always start out with, the first stage is an almost vertical loading of the track surface. The weight on this, at this point, the hoof moves downward at about 10 meters per second, or almost 30 miles an hour, and impacts the top layer of the track surface. During the stance phase, though, the hoof has to actually decelerate from the speed of the horse to stop prior to being able to accelerate the horse forward, right, to propel the horse. So what you see is a pretty dramatic transition here where the hoof is moving downward at 10 meters per second. Then it has to decelerate, completely stop, and then you've got the propulsive phase of the gait where the horse is actually propelling the body forward. And then finally the swing phase, which that's the part of the gait that I can certainly design a track for since it's just flying through the air. If we look at some of the loads we're looking at here, we're coming down at 10 miles an hour, but we only have really the mass of the hoof on there. What happens next is that we actually stop the hoof. We have as much as 4,000 pounds of force on the toe of the hoof. Then the load of the weight of the horse, the dynamic weight of the horse, is then transferred to the track. Then the shear load, or this horizontal component, completely reverses, and that's the propulsive phase. The optimal track then will actually help decrease this deceleration of the hoof during this initial impact, and then will not fail during the propulsive phase where the horse is actually going to move forward. So we've got an optimal. This is unfortunately not something where we can do a safe surface, meaning that we just make it stiffer and stiffer or stronger and stronger, because we really want to decrease that while we're increasing the other. To give you some idea of what it looks like qualitatively, you can see, and this is familiar to most of you knowing horses, but you see the hoof hitting the track. Oops. You see the hoof hitting the track, and you see the small amount of slide during that forward motion. Our system measures the soil under the hoof by simulating the most extreme case, the impact and the loading. Our modeling suggests that properties of the soil more than a foot underneath are critical to the overall performance of the track. This is one of the things that we've seen dramatically out of the synthetic track surfaces is they've solved the base problems in a lot of these cases. We're also seeing more and more of the tracks with traditional surfaces addressing some of these base issues. Without a proper base, we can't have a proper track surface. This is the system. In the past, what had happened was lower loads were used during the testing. These don't affect the measure. These don't measure the effect of the track base. They also have to match the strain rate in order to get the strain rate dependency. So the net effect of this is that we have to have a lot of load hitting the soil fast. And there you can see the dirt moving outward like you do in the thoroughbred hoof, moving outward from the hoof impact. To give you an idea then of how we can characterize these tracks, as I mentioned, we have to have this deceleration of the hoof. That's the shear strength. At the top here we have a fast track, at the bottom we have a slow track. If we measure a particular track, we have a distribution of the measurements on that track. This is a normal distribution that's plotted to the data set that is plotted as dots here. On the horizontal axis, we have both a soft track and a hard track. These are traditionally considered to be a correlated factors, but as we move into more sophisticated traditional track designs as well as synthetic track designs, these are not necessarily correlated. So if we look at that, we've got a distribution of the hardness and a distribution of the shear strength that are measured with the machine. What's critical there to look at is not only the location of this track characterization oval here, but also the size of the oval, because that gives you an idea of the variability as we move around the track. Ideally, this thing moves to a smaller and smaller point at some location to be disclosed in the future based on epidemiological data. So let's take an example here. What happens if we rip, till, and then set a track? You know, this is the standard rip and till procedure, and then being set with a wobble wheel or else a water truck, depending on where you're at. If you look at this, we've got a track that's more to the right-hand side, and more to the bottom. So it's somewhat of a deep track. May actually be a track that we'd be concerned about. For my simple engineer's characterization, this is the soft tissue injuries. These are the fractures. If we look at that, we see we're kind of soft and quite hard. If we rip and till the track, the data becomes this. We move upward and to the left. The track actually got faster in this case, slightly, not a huge amount, but slightly faster as we moved upward. And then we moved to the left and we got softer. But there's another thing to note here. The challenge that we face. What happened was we got it softer, we made it slightly faster, but what do we do? We also increase the variability of the track as we move around. That's what makes this a challenging problem, because we actually need to be able to go through those same sorts of processes without changing the variability. If we look between tracks, which is something that is always a consideration, this is just plotting 5 different tracks that are done. These are actually in 3 different states. If we look at these 5 different tracks, we see quite a large coefficient of variation. One of the things that's consistently shown up more recently is that the synthetic tracks can reduce the variability. If we go back here, that's tightening up this distribution here, which is desirable one way or another, because even if you can adapt your gait to a particular track, you have a heck of a time adapting your gait from stride to stride. So where do we go? One of the things that's evident is that we need engineering support of track maintenance. Synthetic track composition has turned out to be an issue just like track composition is with the organic tracks. There's need for consistent track maintenance, and in traditional tracks there's management of the water and composition. And then ultimately, if I haven't mentioned this before, we have to be driven by the epidemiology. Let me give you 2 case histories of what we've done. Case history 1 is really talking about whether this effect is real. This is basically a short track with good horses. The track had a good reputation with owners and trainers, but there was an uncertain history of a portion of the site. Kind of the classic problems we've seen in different locations in the country are granite ledge or an underground spring. Those are sort of the classic concern. If we look at this, this is the initial data that I obtained on that track. It was measured, it's a short track, it was measured at each 8th mile. We see our vertical load, which is that likelihood of fracture. This is the horizontal shear strength, which is the likelihood of soft tissue injuries in my simplified version. So generally we have a relatively forgiving track. It's pretty fast, but what we've got is very high variability. Diagnosis of that. If we look at a single day, we see that the dynamic shear angle is quite good. Looking at this is a 0.51, which is something we'd consider pretty good. But if we look at the distribution, what we see here is quite a dramatic difference in that area around the quarter pole as far as the peak loads. This is one of the lowest peak loads that had been obtained in testing. So we've got this area of concern that shows up, the quarter pole. So the robotic hoof tester indicated that something was wrong. We needed a tool to look inside the track, and this turned out to be ground penetrating radar. Ground penetrating radar gives us the option of looking at variation in base or variation in the track material. Give you an example, it's basically a skid-mounted radar. We just do a single 4-inch strip, and then we can do circumferentially around the track, and then typically what I do is I also do radial scans out at each of the 16th poles to give an overall view. We obtain reflections at each of the interfaces in the material, and this is the sort of plot that ends up showing up. Typically in the track materials we can penetrate at least 12 to 14 inches depending on clay content. So if we go back to that example case, looking at around the 3/8 pole in the region of concern, what do we see? We saw that the base drops quite dramatically in that same region that we started to get those low numbers. And you can see that there's also variation from the rail out. So this is 5 feet from the rail, this is 6 feet from the rail, and here's 10 feet from the rail. This is a beautiful profile along here, very consistent base, not much variation until you get down. This is quite deep here. Here we're down to 8 inches, and we're still seeing a pretty consistent pattern. However, here, as soon as we were 4 inches down, 5 inches down, we started seeing these dramatic variations. Well, what do? We fixed the problem. This was not let me point out, this was not a problem that was observed based on injuries. We were doing this before we started the injuries. This is our model of proactive track management. The primary tool was the hoof tester. The diagnostic tool is the radar. This is no different than what we do in a clinical situation. Did we save horses? Not necessarily in this case. This was a rather mild situation because we were not seeing a low shear strength that we'd expect. There are also a number of ways to fix the track. The two components are shear strength and vertical modulus, or that stiffness. If we've just got a shear strength problem, for example, a cuppy track, we can simply add fibers, we could add wax, we could add clay, or if we've got our clay content high enough, we can just add water. If we've got a high vertical modulus, we can just add sand. We can reduce the moisture. If it's a traditional track, we can add fibers or we can rip and tilt, which would be what would be done on either a traditional track or a synthetic track. Let me look at the second case history then. This is something that bothered me from day one when I got involved in the track surfaces, and that was that there were two dramatically different maintenance traditions in the United States, if we can put it that way. And these were based on some sort of behavior. And my presumption in this was that it was probably somebody who was pretty good at observational science, who'd been sitting there watching the track for a long period of time, and that's how these must have developed. On the East Coast track, we typically use much lighter equipment. We harrow to a depth of 3.5 inches, and we have sand with a small amount of clay on a hard base. Sometimes on the East Coast they'll talk about setting up a pad, but they won't maintain the pad, so they don't keep ripping it up nightly or weekly like so commonly done in other parts of the country. What I've just based on this, based on my rough calculation or rough assumption, is the California tracks typically use much heavier equipment to maintain their tracks. They use a cutting harrow with a rip to get a pad, so they'll go ahead and use a cutting harrow to rip it, and that's done quite frequently. In some places they'll use a pavement ripper as well. Then the cushion is harrowed daily and between races to a little less than 3 inches. So we have a little lighter cushion on top. Schematically, this is what we look like on the East Coast style track. It's not like the horses are different. We've got the same dynamic load, which is 2 to 2.5 times the body weight. East Coast track, we just have this cushion that's put on top of a base, and it's a little deeper. Here we have the cushion, pad, and base. What I've plotted here in the middle is an estimate of the peak loads moving down from the surface to deep. So what you can see is, before we go any further, is note where the base fits on this graph. The base matters, but still we should understand why that pad exists. Okay, which style is right? This is fine if you've been using it, it's working fine, but as soon as you come up with a situation where it's not working fine, the quick question is, how do we diagnose it? In this case, if a track has a higher injury rate, immediately the question comes up. I can't spell there, but that's the consultant tried but did not get the desired result. And in my assumption, the consultant may also be tired. That's completely possible. And then both track designs developed because smart superintendents saw a need. So which track is suitable for a particular location? Now, one thing that you normally look at is the particle size distribution. This is what's normally reported as the amount of sand, clay, and silt, and sand is normally categorized in several different areas. But what we find is, when we compare the particle size distribution on the East Coast and West Coast tracks, we do not see a significant difference. We see that they'll typically report the clay and silt content, and it'll be 3 to 11%, but there seems to be a fairly random distribution of what track has what composition. However, the real question is the clay different between the East Coast and the West Coast? One thing that's often been claimed is that you can break up sand to get clay, and that's actually not true, because the particle size definition for clay is met, but it doesn't act like clay because it doesn't have the same shape and surface chemistry. Clay can be classified using a polarizing light microscope or X-ray diffraction, with the X-ray diffraction typically preferred. So if we look at the X-ray diffraction, that's what's used for clay mineralogy. We can look at the composition of the clay, and this may be the key to our East Coast versus West Coast designs. We get peaks here, and these peaks are used then to correspond. What's also used is the clay is also swelled in order to in order to see the expansive clays, and then microscopy can also be used to characterize sands. So what I've got here is a comparison of an East Coast and West Coast track, and I'm sorry this is these X-ray diffraction scans, for those of you who are clay mineralogists, didn't come out very well, but I can give them to you afterwards if you really enjoy it. But what turns out here is the East Coast track, if we look down here, in these 3 categories here, these are the clay. Essentially what we can say is on these East Coast tracks, or at least the one I've looked at, we have essentially no clay from a mineralogical standpoint. If we look at the West Coast track, what we see is approximately 5% clay. Bingo, we've got our answer. Why did these develop? It's because of the existence of the clay and the type of clay mineralogy. Now, what happens? We've got a track with concerns. Before consulting on maintenance, the obvious thing is to evaluate the clay by X-ray diffraction. So maybe this is a track that's had a bad meet. They're starting out, or there's some questions from the Racing Commission. If we look at X-ray diffraction, we can say yes. If we get something, we can maintain the pad or end sand, or if we get no, we can maintain it like an East Coast track. So what happens? When we looked at this unknown track, we came up with 8.4% clay. Clearly even higher than the West Coast tracks, even though this was not, in fact, a West Coast track, but a track that had some concerns during the meet. So suddenly you move from maintaining it based on geography to maintaining it based on the clay mineralogy. This is another success where we can begin to say why, because these traditions developed, the traditions are developed based on just observation, but in order to look at these new cases where, for example, there might be a new superintendent or it might be a new track in a new location, the first thing you do is start looking at the clay mineralogy. Okay, so how do we implement this track engineering? My bias is that I think the biomechanical hoof test, because what do we really care about in this whole scenario? What we care about in this scenario is what the horse is seeing. If questions arise, then we need this array of tools. We need to look at base problems. If we don't have a good base, it doesn't matter what your composition is. You're going to have injuries. One of the tracks I looked at, it made no sense to the track veterinarian because one horse had come in with bowed tendons, the next one had come in with a fracture. There's only a couple options for that, a composition variation around the track or a base problem. We have to look at those two and then we can diagnose it. Maintenance protocols, the maintenance protocols matter and they're going to be based on geography. And then the composition. The composition doesn't disappear when we move to synthetic tracks. We still have to look at fiber volume, wax content, and the composition of the filler materials. In the organic tracks, or the traditional tracks, we have the more obvious moisture, organic, and now the clay. So where's the status of our work? The biomechanical hoof tester was originally implemented in 2004, going from track to track. Testing continued in 2005, and we still have a single prototype system in use for track support. What we've got at this point is comparison data is available on about 14 tracks with an additional couple training centers and farm tracks. Those include both synthetic and traditional track surfaces. This needs to be brought to a commercial version, and a partner company has already agreed to partial development costs. The ground penetrating radar is a desirable tool for diagnosing base problems. Basically image before you dig and also continually monitor the base to make sure that it's consistent before you start a racing meet. At this point we have baseline inspection data on over 10 tracks including synthetics. Not that we're that concerned about the bases on the synthetic tracks, all of these are in the US, so they're only a couple years old. What we are concerned about is the ground penetrating radar can also be used for looking at variation of the composition around the track. And then the X-ray diffraction where, as I mentioned, we get to see the difference between the West Coast and East Coast tradition, which now makes more sense. Do synthetics solve all this? Well, I think they've got a potential to be huge. Tracks have been designed, however, for different compositions for different applications, looking at weather conditions. Tracks have in some cases been renovated to tweak the mixture, and then different maintenance has begun to develop in different locales. The risk we've got as people who are concerned about the industry is if synthetic tracks do not solve all of the problems, the suppliers and tracks must be ready to show that the problem is not with the track. So the general philosophy reiterated. We need a common set of measures which we in the industry can agree on that are used to compare between tracks. Horses ship between tracks, they ship between countries. as we develop over time, we should be able to be confident that the horse is going to have a surface that will work. Primary measures should be based on biomechanics. It's difficult when the trainers all ask about whether there's water or sand or silica sand mineralogy or fiber content even. We need to continue to understand why the behavior is different on some tracks, because a lot of this develops for very good reasons, and then provide tools to the tracks to monitor. I want to acknowledge the work on this would not be possible if Dan Fick hadn't ever gotten it started with AQH when he was still at AQHA Racing. The research funding has come from the tracks, a number of the tracks, the Dolly Green Foundation, the Oak Tree Racing Foundation, who have approached this as a research project, which has been an impressive thing for the racing industry. And then I want to give you one more picture of this before I pass off, because this is again another race at Belmont, and this gives you a little perspective on that. So even if the tracks didn't cause the problem, I think they can help improve the situation. And then the remaining question I want to reiterate is none of this is tied to the epidemiology, which is where it has to go. Thanks.